Okay. Let's start. Uh, good morning, everyone. So my name is Manik Kuila. I am a postdoctoral fellow in the group of Professor Subhankar Vedanta. So first and foremost, I want to thank the organizer for giving me the opportunity to share my results. Today's presentation, the title is Conversion Near Control of Spin Orbital Pumping at the interface in CR, CFB, and CR. So, because time constant, I will briefly go through spin orbital Hall effect and their inverses. So, as you know, when a charge current run through the heavy metal like platinum, one can get the inverse. One can get spin current in the transverse direction, and when the spin current is pumped in the this material, one can get the charge current also. So this is called spin Hall effect, and this is called inverse spin Hall effect. Let me select the pointer. So, the basic origin of the spin Hall effect is it can be extrinsic and intrinsic. Intrinsic, like very curvature, induce anomalous transverse velocity, and people mainly use this spin degree of freedom for the spintronic application in the last few decades. But recent studies showed that the orbital current can also be used for the spintronic application. So when this orbital current is the orbital degree of freedom of the electron, so when a charge current flow in the orbital Hall material, one can get similar to the spin Hall effect. One can get the orbital transverse orbital current. So similarly, inverse orbital current can also be detected. So the basic origin of the orbital Hall effect is the orbital texture in the momentum phase when we apply the electric field mainly in the centrosymmetric system, and in case of non-centrosymmetric system, the intrinsic orbital moment is responsible for the orbital current. So now question is how to inject the spin current. So one example is spin pumping. When the ferromagnetic resonance used in a magnetization species, so this precision of magnetization can pump the spin current into the heavy metal like platinum, can inject spin current can convert it to charge current due to inverse spin Hall effect, which can be detected experimentally. And also similar to the spin current, orbital current where the magnetization needs to be high SOC because the spin orbit coupling give the both orbital and spin current. So orbital current can also be generated in the even in the light material in the process of inverse orbital Hall effect. So we are going to use the spin pumping FMR experiment in this talk. I will show mainly the spin pumping FMR experimental results. So these are the experimental technique we are using, the CPW and etc. When we use the nanocollimeter to detect the signal. Now motivation is, as I mentioned, when using the orbital current, one needs to have the ferromagnet with high SOC, or even it should be spin orbit coupling ferromagnet. So the spin orbit coupling ferromagnet, when charge current is flow through, then there is a orbital current, and then this orbital current has to be converted into spin current to interact the ferromagnet. As because the orbital does not interact with magnetization exchange coupling. So in the recent studies also showed that if we put some conversion layer like platinum, tungsten, and etc., one can also use this orbital current, convert it in the spin current here, and that spin current can be injected and it can be used to manipulate the magnetization. So these are the two papers I have shown here. One is the chromium used for this generation of orbital current and enhance the orbital torque efficiency. And another example is TMIGPT copper oxide sample. Here they have shown that using the copper oxide, one can increase the efficiency is way more higher than its normal platinum case. So why we have chosen the chromium is the following. This theoretical paper showed that when the chromium, vanadium, and manganese, these are the transition metal, can be used as a orbital Hall material because its orbital Hall conductivity is way more larger than the spin Hall conductivity. So you may all know that when the spin Hall conductivity and orbital Hall negative spin Hall conductivity and orbital Hall positive spin Hall conductivity in the opposite side of the ferromagnet can increase the efficiency because of the symmetry of the spin current. The spin current is flowing from this side and that side, and if it is negative and positive, it can be additive. So we ask the question: what will happen when we place additional orbital Hall material symmetrically in this structure? So for this purpose, we planned some, we prepared some samples where we use the CFB as a ferromagnet and chromium as a orbital Hall material, and also tungsten and PT used as a conversion layer. These are my final sample structure: chromium, tungsten, CFB, PT, and chromium. So we measure the ferromagnetic resonance. Here the typical ferromagnetic resonance data for this one of the sample I have shown here. And this plot is showing that resonance frequency, frequency versus resonance field plot, which can be fitted with Kittel equation. These are the sample we have prepared. And then this CFB chromium and CFB tungsten chromium, and you can see the delta H variation with the frequency is increasing with the sample structure with introducing the chromium and PT as well. So these are the extracted parameter we have plotted here, and also we measure the sheet resistance of the structure to find out the current of the IEEE or IEEE inverse spin Hall or inverse orbital Hall effect technique to compare them fairly. And the in this message is here is when we introduce the chromium, the Gilbert damping is increasing systematically. When this also platinum is if introduced here, so then this Gilbert damping is increases very much. So now coming to the inverse spin Hall effect measurement results. So these are the typical IEEE measurement which are performed, and the symmetric and anti-symmetric component is extracted from here by fitting, and we plotted the symmetric component with this different sample structure and found out that systematic variation, the current is increases systematically because of the spin and orbital current induced effect. And we plotted the amplitude here again, and this here we can see with the chromium, this charge current, the normal chromium, there is a very small signal of the inverse effective charge current, and when we introduce the platinum, there is a large enhancement of the signal. This might be due to the orbital contribution. So, but upon adding the another conversion layer, the tungsten top, there is a small increase, a little bit of increase, and also we observe with the chromium on the top, there is a no such much increase there. So next we study the thickness variation of the symmetric structure. When we vary the thickness, what will happen in this structure? So we also measure the ferromagnetic resonance, as I have already shown similar data. And here also we have measured this ferromagnetic resonance with these are the curve of frequency versus H resonance, and this is the delta H versus frequency. And with this chromium thickness, one can see the introducing the chromium thickness, one can get the enhancement of Gilbert damping that could be due to the spin pumping effect, spin on orbital pumping effect, and there is a plateau where the 1 to 7 nanometer chromium thickness, there are no such increase in Gilbert damping, but when you increase the thickness further, one can get this increase in Gilbert damping. That can be due to the effect of the orbital effect. Now we also measure the spin orbital inverse spin Hall effect measurement in this thickness dependent data. these are the typical inverse spin Hall effect measurement data showing that the signal is mainly coming from the spin orbital pumping. And this is also, we have plotted the symmetric component. And what we have found here with the chromium thickness, we can effectively, increase the effective current in the structure. That can clearly clarifies that the chromium layer introduce the orbital current in this structure. So in summary, we observe the experimental evidence of spin pumping induced spin and orbital current in the conversion layer, and the orbital current is injected into the spin current, and subsequently it contribute to the charge current through the inverse spin Hall effect, inverse orbital Hall effect. And with increasing effective current is an increasing effective current is observed with the increasing the chromium thickness in the symmetric structure. So further, we want to study in this observation with this STFMR and harmonic Hall measurement, which is under progress. So I would like to thank my professor, Dr. Professor Subhankar Vedanta, for his continuous support and encouragement in this work. And also, I would like to thank all of my group members for their making this environment-friendly lab and their teamwork. So thank you for your kind attention.
Thank you.
So,
Thank you for
now,
your nice talk. So there was now it's our Q&A session, and there was a question from our audience that could you please tell us more about your sample preparation and why you didn't choose tantalum, for example?
Sorry, tantalum. I think
Yeah.
tungsten, right? Okay, why we use
titanium.
tungsten? I'm not using titanium. Can you repeat the question?
From the audience, they may I guess they are questioning why do you choose, for example, specifically tungsten, not titanium?
Okay.
Because typically people could use titanium as a structure.
Titanium can also be an orbital Hall material, but I have already shown in my motivation slide. I can directly go to there. Here. So the reason behind choosing the chromium over the titanium is this orbital Hall conductivity is very high, and the titanium is not that much high, but it can be also used for a titanium. So, and also the tungsten we have chosen because we want to increase the IEEE voltage. That means spin pumping voltage or orbital or even orbital pumping voltage. So as I mentioned, when the positive and negative spin Hall conductivity, here negative spin Hall conductivity is the tungsten, and PT can be the positive spin Hall conductivity. So they can additive in a sense that it can increase the spin pumping or even orbital torque. So that's why we have chosen tungsten as a negative spin Hall conversion material, and as a positive spin Hall conversion material is PT. So someone I think asked why not Mn. So yes, Mn can also be used, but this study I cannot do everything in one way.
Okay, thanks
Any
for
other
your
question?
answering. And I believe there's another one last question.
Yes.
Hi, nice talk. Am I audible?
Yes, thank you. Yeah.
Yeah.
Yeah. Okay. So actually, you have used very thin platinum and tungsten layers, right? Now your
Yes.
exchange correlation lengths are, I guess, more than those thicknesses. So will it hamper, like chromium is generally antiferromagnetic. So will that hamper that antiferromagnetic chromium? Then your CoFeB is ferromagnetic. Now that exchange correlation length, if it is higher than your film thickness, then how will it hamper? If your film thickness, if your platinum spacer or tungsten, if you take it more than the critical length or exchange correlation length, so what will
I
happen?
understand your question.
Yeah.
So actually, if we increase the thickness of the tungsten and platinum, so what will happen? The effect of the orbital, so it may mitigate, because the most of the current generated in spin Hall effect will be dominant. So their orbital may not penetrate, that this conversion may not happen throughout this structure. So reason, as you can see, I can show you the data here. So this can be understood here. So you can see the orbital contribution is here. This PT is using here the thickness, the copper oxide thickness is same, but PT thickness is increases. So in this structure, when PT thickness increases, one can see the orbital contribution is higher, around 1 to 2 nanometers. So and above that, this conversion is not happening. Maybe it's happening, but it cannot actually the torque produce the torque in the magnetization. So that's why I'm using lower thickness just for conversion to see the orbital Hall effect or orbital contribution.
Okay.
So
Okay.
does I okay? Is it
Yeah.
okay?
Thank you so much.